So our next speaker, Frederic Cerou, is going to talk about adaptive replica for simulating reactive trajectories. So it looks slightly different.
Yes,
molecular dynamics is in the, I guess it's related.
Yes, it's the title is a bit different because this one is more focused on something very much specific than the title I gave for the for the organizers. So first of all, I have to say it's a joint work with Arnaud Guyader from Rennes and Tony Lelièvre and David Pommier from École des Ponts Paris Tech. It's still a work in progress, so I will give preliminary results, mainly numerical. So of course it's related to molecular dynamics, so I will first talk what it is about. So we want to deal with models for molecules conformation, I mean large molecules like proteins maybe, interaction between gas particles or even in chemical reactions. So usually it is modeled by, all the information about the system is in potential V. So V is just a function from RD, where RD is the space of all the configurations of the system, into R. And if V is low, then the configuration will be preferred, and if V is high, of course, the configuration will be not very likely. And associated to the potential V, we consider what we call the overdamped Langevin dynamics, which is a diffusion process, so the equation is given here. And so beta is something, is the inverse of a temperature. And of course, associated with this dynamics, there is an equilibrium canonical measure, which is a Gibbs measure with potential V, and at temperature 1 over beta. So this kind of equations and potential can modelize a lot of very interesting systems in real life. Okay, so what we want to specifically to simulate here is I don't see the colors here. Is what we call reactive trajectory. So what is a reactive trajectory? So if we take A and B here, two metastable regions in RD, well, with metastable means if you start in A, your Langevin dynamics will stay a long time in A, and it's the same in B, and both sets will be recurrent for the whole dynamics. And what we want is to simulate trajectories leaving A and going to B without going back to A. So the problem is that if you start in A or near A, you will spend a very long time around the set A here before going eventually to B. So this is typically a relevant simulation problem. And so I would like to notice here that in the molecular dynamics and computational physics community, there were already quite a lot of papers about relevant simulation in this precise context. And I think it's interesting to see what they have done. They have quite a lot of ideas about algorithms and well. So we have to rely here on some kind of relevant simulation to have reactive trajectories. So I have to say that now I will present mainly an application in this context of the ideas Arnaud Guyader explained here yesterday. So I need a kind of a fitting function or what is called importance function in relevant literature. It is, in this context, it's referred to reaction coordinate. So it's just, it can be something more specific for a chemist, but here for me it's just a smooth one-dimensional function with non-zero gradient. And I just assume that A is below some threshold for this function, and B is above some other threshold. A simple example can be just the distance from the current configuration to some reference configuration in A. So we are going to force the particles to go outside A and hopefully reach B in this case. So just to remark here that it is well known that there is an optimal importance function. It is well known also in the computational physics community. So this optimal function is, of course, the probability starting in X to be in B before being back in A. And it is solution of the partial differential equation. And in this context, it is called the commuter function. Well, it's just a matter of vocabulary, but so now I will explain the algorithm. So it's very similar to what Arnaud showed us yesterday. So first I will, so here, the circle here is the surface Xi, my reaction coordinate equals Z min, and this curve here is the surface where my reaction coordinate equals Z max. So we see that B is above some threshold and A is below. I assume I am given some starting point on this surface here, so the red circle is here. And from each one, I'm going to start a trajectory, independent trajectories, until they hit either A or B. Of course, they will most likely hit A first. So these are the trajectories. And then on each of them, I compute the maximum of the reaction coordinate, of the importance function, and I put a point dot every at the first time this maximum is achieved. So it gives me these 3 points, and then I consider the only trajectory was this maximum is minimum. So I take the minimum over all the different trajectories, and it's this trajectory here in red. So this is the only one I will discard at this point. So I consider the level set for my importance function having just this value here, and I'm going to discard the red trajectory here and select one of the succeeded trajectories, so let's say this one, and I'm going to branch a new trajectory at the first hitting time of this surface. So it's here, and okay, and this gives me the blue piece of trajectory, and again I go on until I come into A or into B, and I iterate the process. So I compute the maximum here. I consider the minimum of all the maxima, so it's this one here. I consider the level set, and I'm going to branch another new particle here, and so on. So it is adaptive because I don't have to set the branching levels a priori. So I just computed on the fly one by one. And I iterate the process until all the paths reach sigma max, which was the curve on the right. And I keep only, among them, I keep only those which actually reach B, which which should be hopefully the majority of them. Now I come back to the initialization of the algorithm. So I need some points on the z-mean surface at equilibrium. So I just start a trajectory in A, and I run it for quite a long time. And I keep maybe a subsample of the upward crossing points of the z-mean surface. And I keep also the corresponding piece of trajectory. I'm going backward in time, coming from the boundary of A. And this will give me the first part of the algorithm between the surface z-mean and A. So in this way, I can have a whole family of course not independent, but trajectories from the boundary of A to the boundary of B without going back to A. So it is exactly what I wanted. So a remark here, this algorithm is close to something already proposed in this community. It is known as forward flux sampling, but of course the difference is that what is called here forward flux sampling is the threshold, the branching thresholds are fixed a priori. So it's a more classic important splitting procedure. Well, concerning the diffusion process, it was discretized using Euler scheme, and we have to take care to have a very small time step, because we need that the invariant measure for the discretized process needs to be close to the invariant measure for the continuous time process, for the original one. Okay, so now I will present some numerical results, quite preliminary, but still interesting, I think. So first, a very toy example in one dimension, just to validate against direct numerical simulation. So it's just a double well potential with a saddle point in the middle, so it's something like this, like a W. And I take A to be -1, B to be +1, and the reaction coordinate is just X. And we used our algorithm to compute the distribution of the length, of the duration of reactive path. So here I think in green it is the result from our algorithm, and in red the direct numerical simulation. So naive Monte Carlo, in other words. And so for large beta, they are the same, and for small beta, sorry. And for large beta here, of course, direct computation is much more noisy, because we only have a very small proportion of the sample which actually gets to B. So we have to compute a histogram here with a very few points, and it's much more noisy. And here we have this distribution of times for different value of beta. So I think this one is for 1, 5, 10, 15, 20, the last one is 40. So even for beta equals 40, so where the reactive path is a very rare event, we still have quite a smooth histogram here. So just a small remark here. It seems that these distribution times are distributed have a gamma distribution. Well, I think this might be, for this model, this might be a conjecture. I don't know anything about it in the literature. Maybe it exists, but I don't know. Now a second example, maybe a bit more interesting. So it's not, it is still not a real life example, but it's interesting because it's quite simple in 2 dimensions, but it has an interesting feature. So here my set A will be around a set around this minimum here. The set B is a set around this minimum here. And you can see here that if I want to go from this minimum here to this one, well, I can't go just right in the middle because there is a hill here, but I can go either this way, we take this north route, or this way, I will call it the south route. And depending on the temperature parameter beta, most of the trajectories will go this way or this way. Well, the distribution of the path between the two is it is a well-known feature of this model. The distribution is changes when beta increases. So even if it's a simple model, it's well, it is quite interesting. So we computed here the density of reactive path. So we take the square here and we just divide it in small cells, in small bins, and we compute the empirical histogram of all the reactive paths we have generated, and this gives this surface here. And so this one is for beta equals 1.67. So you can see that both the south route and the north route are used. And here at beta equals 6.67, we can see that the south route is no longer used and all the paths are going on the north route. Well, almost all. This was for this one the reaction coordinate was x, I think, and the next one no. Well, there are two. This one is for reaction coordinate x, and the next one, so isn't much different, is for the reaction coordinate y, I think, or something like that. So just to show that it is not very sensitive to the choice of the importance function or reaction coordinate. On this example, we also computed the flux of reactive trajectories. So it is just done by counting in each cell, in each bin on the square. We just count in each direction the number of trajectories going in or going out. And this way we can reconstruct the flux of the trajectories, which is very important in practical applications. It's one of the things that people really want to compute. And here again you can see a very different picture at for small beta here. So we have trajectories here and here. The flux is the dark blue is a greater value than the light value of the scale here. And if we increase beta, then the flux here is very small, and the trajectories are more this way. What we can see here is that due to the empirical measure of the reactive path and the way they were constructed, there is less, of course, at the beginning there is less diversity in the path. So this is why it is a bit more noisy here. I think we can address this by doing simulation in both directions and take the mean of both, I think, because it's in this case it is completely reversible. So here I just give some typical trajectories just to have an idea. Of course, they are subsampled here because we took a time step much smaller than this. And we can see here that at high beta, a typical trajectory spends a lot of time in the local minima in the north region, of course. So, just a few words of conclusion. It seems to be a promising adaptive method for event simulation, at least in this context. one interesting feature is it's not very sensitive to the choice of the reaction coordinate that we make to do the branching of the trajectories. And especially the reaction coordinate does not need to reflect all the complexity of the system. It can be something quite simple, on one coordinate or something quite simple. So there is an ongoing work on computation of transition times. By transition times, I mean if you start a trajectory in A, what is the mean time it will need to go to B? So this can be in one dimension. This can easily be computed in terms of the probability of the rare event of the reactive trajectory. But of course, in larger dimensions, we have to deal with iso-commuter surfaces, and it's a bit more complicated, and we are working on it. And of course, there is a lot to be done. So the theoretical analysis, which is not done in this context, and to consider to apply our algorithm to more complex potentials, which are really relevant for practical applications. Okay, thank you for your attention.
So is maybe we have time for a quick question.
I'm really surprised by the comment about how robust the results are to the reaction function. I thought you were going to say it was going to be guided by either level sets of the potential function or level sets of an eigenfunction for the diffusion. And I don't know if you thought about. There must be cases where it really matters.
Oh yes, of course. If you there are papers where you can see an example like this, where you have you start here and you have very narrow corridors here, and to go to B here you have to go that way. Of course, if you take something.
That's why, like, level sets of a potential function could be guide. Or
Yes, but yes, of course, there will be cases where simple reaction coordinates will not get to the result.
And also comment on the gamma approximation. Christoph Schutte and I have a paper where we get exponential approximations for exit times, and then maybe that's a building block for trying to get the gamma approximation.
Okay.
Okay, thank you very much.